Hello, welcome to my final project presentation for Applied Optimal Control. My name is Andy, and my project is monopedal movement along single direction with a 3D slip model. So first, a little bit of motivation. Leg robots, compared with wheel robots, often have certain advantages in traversing uneven terrain and navigating complex environments. Now, before controlling advanced leg robots, I think control a monopedal hopper with efficiency could serve as a preliminary requirement. So for this project, what I'm trying to do is to control the hopper to navigate to a certain point in 3D. A bit of introduction of the background. So the model I'm using is called 3D slip, which stands for 3D spring-loaded inverted pendulum model. It is a relatively simple model with only two segments. So basically you have a point of mass, uh, in this case, PS stands for its position, and then a spring that is connected to the mass. The spring itself is massless in this situation, but it can be treated as a robot leg. So the PF right here is the position of the foot, if you would like. In this case, in the 3D case, we also have two different angles. Um, the phi is basically the direction, which is telling you where the robot is facing. And theta is the angle of contact between the leg and the surface. It is mainly used in our control later. So an early application of this model is shown on the right picture. It's called a Weibert hopper. It's developed by Mark Weibert in early 1980s, I think. And basically, he believed in achieving sort of like a dynamic balance. So for this model, there are two different phases. First, the liftoff phase and the touchdown phase. Basically, the liftoff phase is when the robot is in the air and is out of control, basically. It's just like when you're throwing a ball. Once it's out of your hand, the trajectory is basically set. So during the flight, the mass follows ballistic dynamics. Meanwhile, the massless leg is positioned for upcoming stance. This is where the control is. Basically, we need to control the point of contact, the angle of contact during the flight, during when we're in the air. And at this stage, the spring is maintaining its rest length, so it's not having any force on the mass yet. The position of the foot is calculated as shown on the slide over here with some trigonometry. The LH is the length of the spring when it's at rest, and it's constantly changing if you have different angles. And the next phase is called the touchdown. This is somewhat also a free phase because you can't control anything once it's touching down. Since we're assuming that we're working on a perfect environment with no sliding or anything, once you settle with a touchdown angle and it touches the surface, all you can expect is that your spring has kind of forces onto the axes, um, and there's nothing you can do over here. So what about the dynamics of the model? Basically, since we're controlling the position of the hopper, we would have a queue of just the X, Y, and Z positions. And our state is actually the Q and dQ over dt, which represents both the location and the velocity of the robot. Our control input, however, is theta and phi, which is the contact angle and the direction of the robot that I mentioned before. Now, the control only happens during liftoff phase because that's when you can apply torque and change the angle of your leg. Once you're on the ground, you kind of are restricted. So to derive the accelerations of these um, or of the states, um, we have where we can use the Lagrangian mechanics. Basically, since we're assuming that we're working in a perfect environment, there is no energy loss or momentum loss. the kinetic energy and potential energy can convert to each other freely. So basically, we have our kinetic energy as P equals half mv squared, and our potential energy, which also includes the tension from the spring, and our Lagrangian is t minus v. So to derive the acceleration, we can have the Euler-Lagrangian equation. For a more intuitive method, I have displayed the actual derivative over here. It's actually very simple. During liftoff, there is no acceleration on both x and y axes. You only have a gravitational force on the v axis, and that's why basically on x and y, the velocity maintains. And for touchdown, the only thing affecting is the force right here. So K times LH minus L is actually telling you the force that the spring is exerting on the mass. And with that force, you basically separate it into three different directions along x-axis, y-axis, and z-axis. And you have a relative position because you're kind of changing your entire coordinates according to the foot position right here. So how does the control incorporate into this dynamics? Basically, during liftoff, you kind of determine your contact angle, which determines your foot position. That contact angle can lead to xf and yf. And then when it touches down, that xf and yf contributes to the calculation of L, which is the length of the spring. It's constantly changing when it's at touchdown. So to control this, I implemented an model predictive controller. Basically, first you do a dynamic linearization. You write your derivative of state as a combination of the state itself and the control input. And then I have defined my cost function as a combination of optimal trajectory with minimum effort. So on the left side here, the optimal trajectory is basically the square of the error between the current state and the desired state over time t. And the minimum effort is basically your control input. Why? Because in the real life, normally torque is directly related to angle. The less angle you change, the less torque you exerted, hence the less effort. So for minimum effort here, it's also reasonable to use just the angle itself. So for constraints, there are multiple constraints actually when doing the trajectory generation with the ODE function in MATLAB. For example, the z coordinate should always be positive, and I have like two different event options that determines when the switch of phase happens. Basically, there is a requirement that you meet when you change from liftoff to touchdown, and the requirement when you change from touchdown to liftoff. But for the controller, the main constraint is actually the contact angle. The direction doesn't have a constraint because literally in 3D, the robot can be facing anywhere. It's moving freely on the horizontal face. And for the contact angle, I've manually set it to be within 0.7 because normally a large theta could lead to faster convergence or faster locomotion, but also it could lead to imbalance. Oftentimes for this touchdown, if you use a very large angle for the next touchdown, you might not be able to recover that imbalance you caused for this touchdown, and it's not good for the trajectory optimization. So the manual threshold is set to implicitly ensure the maximum speed of the hopper. And this is my result for a desired state of 2010. That is on x, dx, y, and dy. I don't have a desired state for z and dz because the hopper is naturally jumping up and down constantly. So on the z state, you can just see it's hopping. But on the x and y you can see that it's converging to the desired state, both on position and velocity. So you can also see there are some linear segments on the on both graphs. That is perfectly normal. As I said before, this is just indicating that it is in the liftoff phase because at that time you can't change anything but the contact angle. So the speed remains, the position is like linearly changing. And finally, some animation. So this is the starting position and this is the target ending position. As you can see, it is jumping. Let's see it again. So, and then here you can see the X and Y position changing. Um, uh, if you watch closely, this is very near to my constraint set here. Okay. So a bit of conclusion. Basically, the result shows convergence to the desired state with constrained control input. Uh, More can be expected in the future as an extension of this project. For example, minimizing the convergence time. Currently, I am setting the time horizon to time horizon, the whole time for optimization as 10 seconds. But as you can see in the graph, it is having some sort of a stable state at 8 seconds already. So a possible extension is to find the minimized convergence time in the cost function. Another one is to follow a preset trajectory. Currently, I am just doing it, moving it from point A to point B, but we can also have a trajectory to make the hopper to follow. And last, we can, instead of manually setting the constraints, we can sort of have a way to determine the contact angle constraints with learning methods. And thank you. That is my presentation.